On behalf of CAETS 2021, allow me to give a warm welcome to Roberto Carnicer from Academia Nacional de Ingeniería, Argentina, moderator of Technical Session 4, Oil and Gas.
Good morning, ladies and gentlemen. My name is Roberto Carnicer, member of the Argentinian Engineering National Academy. It is my pleasure to open session 4 regarding to oil and gas for CAETS 2021, the future of energy. Today, the world confronts us at a crossroad difficult. On one hand, the future of fossil fuels that allowed the world to grow extraordinarily, achieving substantial improvement in the quality of life all over the world, both in the West and in the East. And on the other hand, the responsibility of all in the face of climate change. How to continue growing so that in future generations, a larger population can continue improving their standard of living with economical, accessible energy resources and with the least possible environmental impact. Technology is what will serve as a bridge between these realities. We could ask ourselves many questions about how to realize this urgent need to reconcile energy with climate change. Are all the countries in the political, social, and economical condition to achieve this objective? The impact of the energy cost can be afforded by everybody. Today, we are presented with this challenge, which we must face. Once again, the human being will be able to overcome it, as the history of humanity shows. In this session, we will have the opportunity to listen presentation on this topic by international experts. They know and understand the problem and feel the responsibility to share the vision to us to get closer to a possible reality. It is an honor for me to present the group of speakers that will join us in this session. They will talk us about several important issues. For example, how oil and gas producers will be part of the solution. How will be the future oil producer strategy to combine hydrocarbon fuels with climate change? In the sense of technology, how to develop a low carbon transport sector, the impact of the carbon capture technology, its efficiency and cost, and finally, the role of natural gas in the transition. How relevant natural gas is in the speed and implementation of the transition. And finally, the use of natural itself synergizing the reduction of emission. Here, I will do briefly this presentation of all the speakers. First of all, we will have Dr. Bassam Fatou, Director of the Oxford Institute for Energy Studies and Professor at the School of Oriental and African Studies from the London University. He will talk us about the energy transition and oil exported adaptation strategies. Then Dr. Frank Behrendt from the Institute of Energy Engineering at the University of Berlin will speak about oil scenarios, future components, technology option for a low carbon transport sector. Engineer Andy Kalitz, Secretary General of the International Gas Union, will present the natural gas transition and the role of gas as a bridge in this energy transition. Michael Stopper, Chief Strategist, Global Gas Energy at the AHS Market, will talk about gas and climate change, and gas will become the second pillar of the decarbonization alongside renewable power. From the perspective from Australia, we are going to have Dr. Roberto Aguilera, Senior Research Fellow from the Carleton University, Australia, where he will describe the impact of the gas and LNG growth, the coal replacement, and how the energy growth will be covered during the transition. In the last two presentations, we are going to have Dr. Franklin M. Orr, Keeling and Carletonville professor at Stanford University, where we'll talk about carbon capture and storage, all the several alternatives of CCS, the use of CO2, and option for geological storage. And finally, with a different view and important perspective, the natural one, is Mr. Dr. Fraguillo, director of the Carbon Group. He's going to talk us about nature-based solution, mitigation emission and sequestering carbon through natural-based solution and without increasing cost and users. So we are going to have a tremendous intersection by the level of the speaker and the challenging topics to develop. Let me ask you a recommendation. I would like to encourage the audience to submit written questions to the panel through the Zoom chat during this meeting, and we will address them after the presentation. Thank you very much. I leave you with the speakers.
It gives me a great pleasure to be joining you today. What I would like to do in my presentation today is to divide it into two parts. In the first part, I will talk about what are the main features of the energy transition that I think are quite important in shaping oil exporters' strategies looking forward. And then in the second part, I would look at some of the adaptation strategies that oil and gas exporters actually can use in order to deal with the repercussions of the energy transition. So let me start with the first theme. I don't have my own demand projections, but I can make few observations about oil demand looking forward. The first observation is that oil demand projections are extremely sensitive to the underlying assumptions of the model. This could be economic growth, population growth, transformations in the transport sector, the global carbon taxes. By changing any of these assumptions, one can push the peak forward or backward by decades. Also, it depends very much on the purpose of the exercise, whether it's about forecasting or backcasting. What do I mean by backcasting is when the modeler assumes that a certain outcome will be achieved, let's say net zero by 2050, then it works its way backward in order to identify what it takes to achieve a certain outcome. Also, most of the scenarios tend to predict that there is one unique global peak, after which oil demand will decline sharply after reaching that peak. Although, we could see a situation where oil demand actually could plateau, or actually we could see a situation of multiple peaks. Now, what's quite important to note is that there is no consensus in many of the underlying assumptions. Some of the projections are based on historical trends, which show that fast transition in the energy system has rarely happened. Other projections are based on the fact that this transition is unique. It's about fighting climate change, and it's basically driven by government policies. Now, I think there are few features of the energy transition that are worth highlighting, and in my mind will shape oil exporting country strategies. The first one is that the speed of the energy transition is highly uncertain. The second one is that the transition will not be uniform across the globe. The third one is that transition will not be linear. It could actually be disruptive. It could be subject to setbacks. And finally, that there isn't a single transition path. And I will revisit this topic towards the end of my talk. However, regardless of the speed of the energy transition, its impacts are already being felt. The perceptions and players' behaviors are shifting much faster than actual changes in the energy mix. And this is already shaping the energy industry on some key decisions. For instance, in terms of finance, one can think about how the energy transition is already affecting investors' risk preference, financing costs and availability of finance for hydrocarbon projects. We also see changes in the players' behavior. Look at the international oil companies, the way they are adapting their strategies. They're incorporating climate-related objectives into their strategies. They're trying to reduce the share of oil assets in their portfolios and trying to shift more towards natural gas and renewables. And many of these companies has also recently announced very ambitious targets to reach net zero emissions by 2050. For oil exporters, these challenges are actually much more pronounced for a couple of factors, depending, of course, on the country context. The first one is that the proved reserve to production ratios extend for multiple decades, so they face the challenge of monetizing a very large reserve base. The other important factor is that there's a risk of losses in export revenues, and that could disrupt their socioeconomic well-being, given the high reliance of their economies on oil revenues. So a key question to my mind is, what adaptation strategies should oil exporters pursue, given that there are domestic economic and political constraints, an energy transition which is changing the prospects of oil demand, but whose speed is uncertain and whose impact is not uniform across the globe, and also at times when the perceptions and policies are changing very fast. So one effective strategy is to diversify away from the oil and gas sectors. But there are real challenges to realize meaningful diversification, particularly fiscal diversification, the heavy reliance of government spending on oil revenues. Achieving diversification requires building human capital, improving education system. It requires extensive structural economic reforms. It requires transparency on governments and removing barriers to the private sector participation. And there is uncertainty about how quickly these reforms could be implemented in many of the oil exporting countries. But in addition as well, one needs to recognize that the oil and gas sector remain very profitable and still enjoy higher margins than those sectors that some of these countries are trying to diversify to. Also, one has to take into account that we could see reduced investment flows into the oil and gas sector, and this can cause supply to fall faster than demand, resulting in high margin, at least for short periods of time. Also, governments in oil and gas exporting countries need to leverage on oil and gas revenues to ease the pain of structural reforms. So that's why exiting too early from such an established strategic sector deprives the country of an important source of income, but also quite important from a key source of competitive advantage. So the question then becomes, if diversifying from oil and gas sector is suboptimal and it cannot be achieved at a rapid pace, how to enhance the competitiveness and increase the resilience of the hydrocarbon sector in a world that is transitioning towards net zero emissions. Some oil exporters can compete on cost and can actually take measures to improve the efficiency of production and lower these production and extraction costs even further. Other countries can adopt faster monetization strategies. However, lack of fiscal diversification and the fact that the social cost of production is quite high act as a constraint on this strategy. There will be some countries that are able to increase supply, but at the end of the day, in the face of a slowing demand, this would result in lower revenues, at least in the short term. In the longer term, some countries, might be able to capture market share, and that could offset the reduction in revenues due to lower oil prices, but not a lot of countries are in a position to do so. Also, one needs to take into account as well that importing countries may decide to implement higher carbon taxes, and this could create a wedge between the revenue generated by the oil and gas exporters and the revenue generated by consuming countries, with consuming countries actually capturing a big part of the rent. So in short, there are limitations to this strategy. Another strategy is to try to diversify into products and exports which are closely related to hydrocarbons and invest in energy-intensive industries such as petrochemicals, steel, cement, and fertilizers. These could add higher value-added products, and they could provide a hedge against price volatility. And the development of such sectors can also produce some technological spillovers. But again, heavy industrialization into energy-intensive industries increases the domestic emission of greenhouse emissions. And it's also possible that importers can develop policies to account for carbon content of final goods, and they can decide to apply border carbon adjustment measures, again capturing part of the rent. So that is why it's very, very important that oil exporters and gas exporters to compete on dimension other than cost, and particularly on reducing emissions. Exporters could work towards ensuring that their production processes and core hydrocarbon products can compete on the emissions front. This involves reducing emissions in the production process, Scope 1 and Scope 2 emissions, and also in the consumption of gas and products derived from crude and natural gas, Scope 3 emissions. And there are some oil and gas exporters, such as Saudi Arabia or Qatar, which are in a very good position compared to other producers, either due to the low carbon content of their crude or to the fact that they have invested heavily in infrastructure to reduce gas flaring and methane emissions. The real challenge really lies in reducing emission from consumption of final products. And that is why it's very, very important to look at strategies which could enhance the resilience of the energy sector. And in my view, one really needs to look at mitigation strategies where oil and gas exporters could have some comparative advantage. And one of those areas is carbon capture, utilization, and storage. It's actually, CCUS is an essential to reduce emissions from hard-to-abate sectors and is quite an important technology to reach net zero targets. But this is also a sector where some oil and gas exporters could have some competitive advantage. It can help maintain oil and gas in the energy mix for longer. It can also increase the competitiveness of their energy-intensive industries, and it could result in further integration of the energy sector. For instance, by capturing CO2 from energy-intensive industries and using them in the oil and gas sector for enhanced oil recovery. However, despite the strategic interest for oil and gas exporters to lead on carbon sink mitigation strategies, most of the CCUS projects at the moment are located in OECD countries. And most of the support schemes are most developed also in OECD economies. Now, from an oil and gas exporter, investment in CCUS lowers the return compared to existing strategy of exporting unabated oil and gas. But it's quite important to treat this cost as being important to improve the resilience of the energy sector. Having said that, shifting the cost to oil and gas exporters alone is not viable, especially if these costs are too high. Producing countries, after all, are likely to be the most affected by the transition, and they're likely to face much stiffer competition for limited funds. And that is why I argue that burden sharing mechanisms should be developed to enable a much more inclusive path. And at the moment, there are various proposals that are being looked at, such as the wellhead carbon taxes, creation of CCS clubs, creation of carbon storage units. I'm not going to go into the details in the limited time that I have, but these policy framework could develop, and they should be developed within the Paris Climate Agreement. So let me conclude with this final slide. Some exporters are willing to be part of the solution, and they are leading on initiatives to fight climate change, and OECD countries should build on this momentum. However, there must be a recognition of national circumstances, the fact that there will be various transition paths depending on starting points, core competencies, and existing assets. Insisting on a single path could delay the transition. It will not enable the use of the technical and financial resources of producers. It could perpetuate non-cooperative behaviors on negotiations, and it could increase the cost of the transition. And it's quite important also to provide frameworks that don't discriminate against certain technologies or fuels and allow technologies to compete. And one important aspect as well is to develop burden sharing mechanisms between importers and exporters and try to integrate them into multilateral and bilateral frameworks. But at the same time, oil and gas exporting countries need to show leadership in mitigation technologies and push from frameworks that promote burden sharing mechanism and realize that the competition is not only on cost, but it has basically to enhance, to compete in addition to cost, also in emission reduction. And with that, I conclude. Thank you very much for your attention.
So, ladies and gentlemen, welcome to today's presentation here on oil scenarios and future components for oil scenarios. The title may sound a little bit strange, but I will try to introduce you a little bit into the field of synthetic fuels, and I will try to give you some insight into possible ways making synthetic fuels, will demonstrate alternative pathways, and will demonstrate what kind of alternative results we can expect for certain pathways. When talking about climate change, the question is, what is the influence or what is the part transport has in this climate change situation? Here, numbers for Germany from the year 2019. Transport in Germany contributed about 19% to the overall greenhouse gas emissions in that year. The biggest block was still energy with about 36%, industry 22%, and the rest was of a smaller order of magnitude. A number of 19% for transport is not untypical for an industrialized country. Countries like the US, where long distance heavy truck hauling does play an important role, may have numbers between 25% and 30. But it's the same order. And so consequently, transport is a significant contribution to the overall greenhouse gas emissions. And we have to be very careful about finding ways beyond thinking about a transformation to battery electric vehicles alone, because that will be available in a few years or even decades out. And in the meantime, we should try to minimize the amount of greenhouse gas emissions based on fossil carbon-based fuels or crude oil-based fuels by replacing this type of fuel for internal combustion engines with fuel where fossil carbon doesn't play a role. Looking or breaking down this 19% a little bit further down to, we will see about 60% were passenger cars, buses and trucks were about 1/3, 35%, and everything else, shipping, domestic aviation, shipping, rail, maritime traffic within Germany was a small 4%. So dealing with passenger cars and preparing fuels and making fuels available which are not crude oil based does contribute overall to roughly 10% of German greenhouse gas emissions. And so it's an important part. It's not solving all problems, but it's a contribution we have to take care of. Quite often, the discussion about the greenhouse gas emissions and the transport system is very much focused on the fuel or the type of engine we use. But we have to separate two aspects here, and I will start with the one which is less popular in the discussion in our community, and that is we also have to look into changing the way mobility is organized. One important question is, here on the left-hand side, are we able to reduce the transport demand? But here's a clear conflict between what we call globalization, moving goods between continents due to the better availability of certain goods in certain locations, better pricing. The question is how this moving around goods on a global scale will be changing in the future with increasing CO2 prices, making the transport more expensive. So the question is, are we able to reduce the overall amount of kilometers or miles driven or a good is transported? Then the question is, what kind of modes of transport will we apply? If you look at a land transport, will heavy trucks be a dominant part in the future? Will we be able to move part of this transport of goods to the railway systems? And other things apply also to the local area, public transport versus private transport. And so when talking about minimizing or reducing the overall greenhouse gas emissions from the transport area, looking into this aspect is also a very important part, but not part of today's presentation. When talking about the immediate influence of transport to greenhouse gas emissions, we in many cases talk about increasing the efficiency of a vehicle, making it consume less fuel per kilometer driven. But also, and that will apply to the future in a higher degree, is we have to reduce the amount of carbon, especially fossil carbon, of the fuel used. And consequently, we should try to move away from crude oil-based fuels to fuels where the carbon does come from different sources. And that is in the focus of today's presentation. Legal requirements in Europe, but similar rules are on their way in other countries as well. Until recently, until 2020, 130 grams of CO2 per kilometers were allowed. In the current period between 2020 and 24, this value has gone down to 95 grams of CO2 per kilogram, and it will drop down to below 60 grams of CO2 per kilometer. That is a significant decrease, and it is not achievable by simply making engines, internal combustion engines, more efficient. You have to include also biogenic fuels or synthetic fuels where the carbon is not from fossil sources. And one has to keep in mind, despite the discussion how much CO2 is emitted in the production of a car, both internal combustion engine driven and battery driven cars, about 80% of the CO2 emissions result from the driving phase, from the use phase, so are closely coupled to the fuel used in driving this car. So greening or making this less fossil is an important step to be done. Looking into technology options for a low carbon transport sector, a very simple, straightforward way is using biogenic fuels, bioethanol, biodiesel in a internal combustion engine. The problem is that in many cases you have this well-known competition between the food use of grains of starch or food use of oilseeds and the fuel use. And so that is a very hotly debated topic here. So we have to look for alternatives. And when we look at renewable sources of fuel, we can start with electrons generated in photovoltaic systems, windmills, hydropower systems, and can store them directly in a battery and then drive an electrical engine. So that is the most straightforward way with overall efficiencies around 70%. Or we can use the electrons generated from renewable sources, make hydrogen, store the hydrogen, and then use the hydrogen to drive a fuel cell. Or further down the road, here we have efficiency around 30–35%. Or we use hydrogen together with CO2 from the air or captured by CCS systems and make synthetically, mostly driven by catalytic processes, methane or liquid fuels, which then can be consumed in an internal combustion engine vehicle again. And the pathway we are looking here at today is the pathway leading to liquid fuels, liquid synthetic fuels without fossil carbon involved. When we look at fuel designs, we have two components which are of importance. First, the car maker has to know which kind of fuel is needed to allow the engine to perform as expected. We are talking here about energy density, knock resistance, emissions, compatibility with other fuels. So the term drop-in fuels comes to my mind here. So the adherence to standards. And the other question is, are these alternative fuels available globally? What is the legal framework for this? Sector coupling comes into play as well. On the other hand, the fuel manufacturer, the refinery, has to understand how a CO2 free production of fuels look like. The question is, how can a process be developed? How can a process which may be viable in a lab scale be transformed or scaled up to industrial size? What is the economic efficiency of the process? And the question is, are those processes environmentally benign? Is social acceptability certain kinds of questions? So both parties, the car makers as well as the refineries, have to exchange information and have to strongly cooperate on this in aiming at the same target, making high performance renewable fuels available. A short dive into chemistry here. What makes a typical fuel which is used in today's, and we are talking about petrol here for spark ignited engines. So the base fuel in many cases is something of the C8 component, isooctane shown here. And then you have some other components, I will not discuss details here, which needs to be added, because otherwise the combustion behavior would not work out. You have to make sure that the density is similar. You have to make sure that the vapor pressure is fitting. You have to play around with the knock resistance. And here, fuels containing O atoms are very helpful because they are very knock resistant, avoiding damage to the engine. And here, some higher hydrocarbons have to be added again for boiling point matching and making the density adhering to standards. So whenever you come up with a synthetic fuel from pathways I will discuss in a minute, you have to make sure that these types of components are present, because otherwise the fuel you create will not adhere to standards that are in place for petrol, and the standards are important for the proper operation of the engines. There are lots of ways to create mixtures of hydrogen and carbon monoxide, which is a key component in making either a Fischer-Tropsch fuel or a methanol to gasoline synthesis fuel. So we have to find ways preparing this. And I will only discuss one pathway here because all these ways have certain advantages and disadvantages. And one important step is you make an electrolysis process, splitting up water by using electrons from renewable sources into hydrogen and oxygen. The oxygen can be used elsewhere. You take the CO2 from the air or captured using CCS systems. The CO2 can react with part of the hydrogen, forming carbon monoxide and water. Water is moved away, and then you have an adjustable mixture of H2 and CO, which then can be used downstream in the synthesis processes, resulting in the synthetic fuels we are aiming at. As you can see in this picture and the next picture, there are lots of variants how to combine the preparation of the H2 and CO mixture from the original water and CO2. But the one I just discussed is the most important one, and that one which is technically most advanced. I already mentioned, we have two pathways which are looked at in detail. One is called Fischer-Tropsch synthesis. That is a synthesis method which has been developed in Germany in the 20s of the last century and has been applied in South Africa for quite a while and is used today for a number of other purposes. Essentially, you allow one molecule of carbon monoxide to react with two molecules of hydrogen, resulting in a long chain hydrocarbon and water as a byproduct. You have the synthesis step here. I don't want to go into detail. Then you apply a distillation step. You separate all the components, and those are abbreviations of the components I mentioned on the slide a few minutes ago, which form a typical petrol-like synthetic fuel. Yields are around 80 to 95%. It's a catalytic process. slightly elevated pressure and temperatures. Different types of reactors are involved. It's a well understood synthesis process and a well understood downstream resulting in the products in the distribution we do need. The alternative doesn't make the long chain hydrocarbon, but in the first step results in the forming of methanol, CH3OH, which then is transformed into dimethyl ether, DME, which can be used as a drop-in fuel as well. Or you apply another catalytic step, again making long chain hydrocarbon, which then are brought to the same refinery after treatment, resulting in the same set of products. Here, the processing conditions with respect to the pressure are very similar. Temperature is slightly higher, but there are certain differences in the process with result to the output. And this is collected here. Both processes have a very high technology readiness level. Fischer-Tropsch is state-of-the-art. Methanol to gasoline is not far away from this. The interesting difference is that the selectivity with respect to the fuel at the very end, in the best case for Fischer-Tropsch, is around 40%, while in the case of methanol, it's significantly higher by about a factor of 2, around 90%. And consequently, also the carbon efficiency defined down here is better. So as a consequence, the chemical or the energy efficiency resulting in the final fuel in this mixture, which could be a substitute for standard petrol, is about twice. And that is a consequence of the higher selectivity. It goes down here. And the energy consumption per megajoule of product is about the same. But the tricky part, the energy consumption per megajoule of the target fuel is significantly lower for the methanol to gasoline process, simply because here the overall selectivity is higher. So looking at this from a refining process, this pathway is much more interesting because it results in higher percentages of what we are looking at, making it energy-wise more efficient and also cost-wise more efficient. What is the potential, positive potential of fuel design? Compared here are a standard petrol adhering to the European standard 228. That is what is described for spark ignited engines. Particulate matter can be significantly reduced by this kind of fuel, simply because here the oxygenate content, so the oxygen content, helps to avoid forming of particles. There is a certain reduction in nitric oxides, a certain reduction in hydrocarbon emissions from the engine. And now when the carbon comes from renewable sources, essentially the greenhouse gas emissions, the CO2 emissions from fossil sources drop down to zero. But even if the carbon is from different sources, the synthetic fuels tend to be more effective. So with synthetic fuels, standard emissions can be reduced. And when the sources of the carbon is from renewable sources as well, almost no new CO2 emissions are released to the environment. Let's sum up for a moment. The study I quoted here on some of the slides clearly showed that modular petrol synthesis from a number of components as listed on an earlier slide can be used to come up with fuels which adhere to the standard, which is an international standard, there's an American standard corresponding to this. And we have seen that this methanol to gasoline pathway, due to the twofold in selectivity, results in significantly more efficient and cost-effective pathways. Synthesis costs are around €1 per liter, which is still too high compared with crude oil-based fuels. But we have to keep in mind, in this case here, no CO2 price would be applied when this fuel is taken from renewable sources. So, and this offers a roadmap for CO2 emissions at a significant level, even for internal combustion engines, helping to create a transition pathway from today's situation to one where no relevant CO2 emissions from the transport sectors will be observed anymore. And with this, I would like to conclude my presentation and thank you very much for your attention.
Ladies and gentlemen, it's a pleasure to speak to you today about the important role of gas in the energy transition in the world. Whilst I'm presenting today, gas is cooking meals for families. Gas is heating baths and showers for children and their mothers and fathers. It is making glass for our houses, for our kitchens, for our offices, and for our pharmacies, including also cutting borosilicate for COVID vaccine trials. Gas is heating schools and universities and hospitals and hotels and offices for students, for patients, for guests, and for workers. And gas is baking bricks for people's houses. Gas is generating power for citizens and businesses in cities and is transporting our imports and our exports between continents. It is heating metals for manufacturing our cars, including electric vehicles. It is delivering goods to our homes and businesses and offices. It is processing food and baking cakes for children and for adults. It is making fertilizers to produce our food on our farms. It is making paper for our books and parcels and offices. And it is making aluminum for our aeroplanes and cars and buildings. And it is making steel for our railways and our buildings and our vehicles. So natural gas is a widely available, deeply trusted and versatile energy source, likely to grow to being the largest source of primary energy in the world. But looking to the future, the greenhouse gas emissions from natural gas, when consumed, also critically requires hydrogen to also play a role in the energy transition which lies ahead for us. If we for a moment just look at the global total energy scene, gas constitutes 24% of primary energy, oil 33%, coal 27%, nuclear 4%, hydro 7%, and renewables constitute about 5%. And that role of natural gas means that 4 trillion cubic meters of gas is used every year. It is consumed in 110 countries. It is exported as LNG by ship from 21 countries to 42 and rapidly growing more importing countries. It constitutes 24% of primary energy and 23% of global power generation. And that is done in 1,700 gigawatts of gas-fired power. But the outcome is also that 7 to 8 gigatons of CO2 is produced per year, whilst the world looks forward into the future with 50 years of proven reserve divided by current production. And so the question is often asked, what will be global supply of energy in 2050? Where will renewables and hydro and nuclear and coal and natural gas and oil go in terms of their importance as energy sources as we consider not only global energy supply, but also various rapid transition scenarios or net zero scenarios or business as usual scenarios? And the reality is that the energy supply system of the future and the role of natural gas is not known yet because there are a number of unknowns. The first big unknown is what energy efficiency gains will the world make in terms of the total energy demand of the world. The second big unknown is what will happen in terms of nuclear expansion. The third one is what will happen in terms of transportation mobility by air, by sea, and by road, and what inroads will electric and hydrogen mobility make? Will we be able to scale up carbon capture? Will we be able to manufacture in large quantities green hydrogen at acceptable economics? How much battery storage will be installed? What will happen in the big industrial, energy-hungry cement, steel, and ammonia sectors? But what is very clear is that during that period, of the next decades, natural gas is going to play 10 critical bridging roles. And let's remind ourselves what a bridge does in our society. A bridge connects two places that are impossible or difficult to travel between. And bridges often last for a very long time. Gas is going to have to bridge between a world with coal in power industry to a world without coal. Gas is going to have to bridge to allow the current generation of old nuclear reactors, more than 30 years of age, to be phased out and replaced. Gas is going to have to bridge in a power sector today globally where wind and solar has to grow 10 times to that capacity. Gas is going to bridge between very insignificant utility scale battery storage in the world to a later time when installed battery capacity has been significantly increased. And gas is going to have to bridge between the current development of shallow onshore wind and offshore floating wind. Gas is going to have to bridge between the current power grids of the world and reconfigured, strengthened power grids that can accommodate remote renewables, that can deal with power system stability challenges, stems from not having rotating steel to keep the world's electricity system frequency at 50 or 60 hertz. And gas is going to have to bridge between gray and blue hydrogen of the first phase of hydrogen development to a future of green hydrogen, including building the necessary transmission and distribution networks. Specifically in Africa, gas is going to have to bridge between deforesting for coal and light and Africa energized by gas and renewables and cooking stoves. And gas is going to have to bridge between a period of poor air quality in China and India and the rest of South and Southeast Asia today, and a future where it is much improved. And as far as the new equipment for the future is concerned, gas is going to have to bridge to help manufacture and provide the energy for wind turbines and batteries and solar panels and copper and steel that have to be produced for the energy transition. Against that global background, let me turn for a moment in closing to Argentina. If we look at the Sankey diagram with energy production in Argentina on the left and energy consumption in Argentina on the right, it is very clear that Argentinian oil production plays a key role in meeting the energy needs for the transportation sector in Argentina. It is clear that significant gas production plays such a key role in the country to keep its energy industry going, to keep its electricity industry going. And we see the reliance on natural gas-fired power. And it is also true that in 2021, there is negligible hydrogen and negligible battery storage installed in Argentina, like in every other country. And if we then think about the future of the energy transition in Argentina and the role that gas can play, it is clear to me that Argentina is absolutely blessed with subsurface resources that could be the foundation and the catalyst of a true gas economy and a major role in enhanced sustainability and a significant economic driver. But this cannot just be about Argentina. It has to be about the region. Gas inevitably is a continental play, whether you think about the Yamal in Russia, or you think about the Bakken in the United States, or the South Pars and the North Field between Iran and Qatar. Argentina has to think big. And on top of that, what can't be done by pipeline has to be done by liquefied natural gas, which globalizes the gas industry and the global market. And it is important that Argentina thinks in both pipeline solutions and energy solutions for the future. Then it brings me in closing to hydrogen. Hydrogen and gas are soulmates in the industrial future, where infrastructure has to plan for methane today and for hydrogen tomorrow. And it is important that Argentina considers that. There can be no successful energy transition, neither globally nor in Argentina, without gas. I thank you for your time today. Have a great day.
Let me start by thanking very much the National Academy of Engineering for this opportunity to join the conference, to join this panel, and to give you a presentation. And the topic that I have been set and which I am delighted to address is gas and climate change. I think we all understand well that the issue of climate change and the associated issue of the decarbonisation of the energy system is one of the great challenges of our age. And I will be suggesting to you or proposing to you during this presentation that gas can and gas needs to become the second pillar of decarbonisation efforts alongside the existing pillar of renewable power. More specifically, I will be making 3 points. First of all, I will point out 5 ways in which natural gas can help deepen and help push further the process of decarbonisation. Secondly, I would like to point out how the pathway for emission reduction is of critical importance. And here I will suggest that gas and natural gas can help in a very important way. And thirdly, I will argue that there is a natural transition to move us from fossil fuel natural gas to low carbon, zero carbon gases that will avoid the concern that is sometimes raised of lock-in of fossil fuel emissions, which we believe can be addressed and can be avoided. But before we go there, let us start at the starting point here, and let's just remind ourselves of where we are today and the challenge we have. I'm showing you here energy sector GHG emissions, CO2 and methane emissions combined. I'm showing you by fuel and by sector. And if we look by fuel, you can see that natural gas today accounts for approximately 8 gigatons out of a total of 37 for the energy sector. And that coal is, of course, the biggest single contributor to emissions, to just over 15 gigatons. That's if I add in the combustion and the fugitive emissions together. And if we look at the sectors, we can see that the largest sector is power generation, where the emissions are coming by and large from coal and natural gas. And the hope would be, or the plan, of course, is to replace as much as possible with renewable power. From transport, where the emissions are coming predominantly from oil, and where part of that transport, the hope would be to turn it into an electricity demand back into the power generation sector by bringing in electric vehicles. And thirdly, the third great sector of emissions, the industrial sector, where we have a use of coal, a use of natural gas, and a use of oil, but in which natural gas plays a particularly important role. Now, the 5 ways in which I would suggest to you natural gas can play a very positive role and support the push for decarbonisation are shown with these 5 arrows. The first one, which has been much talked about for many years, but is becoming more and more urgent, is the idea of fuel substitution away from coal and away from oil and towards natural gas. We can get approximately a 50% saving if we move from old coal-fired power stations to best-in-class modern natural gas plants. A smaller emission saving, maybe around 20% if we are displacing oil. Point number 2, decarbonization scenarios naturally rest upon an assumption of a significant adoption of electric vehicles. That means a significantly higher demand for electricity, and here natural gas will support and will need to support renewable electricity to meet that burgeoning extra demand. I mean, it's tough enough to meet the organic growth in electricity demand. We still have huge parts of the world without any electricity at all. We need to give electricity to many poor and emerging countries, and then we need to provide electricity to allow the adoption of electric vehicles to take place, and natural gas can help us there. Thirdly, carbon capture and storage can help keep fossil fuels in the mix and can help support industry. And natural gas is going to be the big driver and beneficiary of this. An abnormally large number of hard to decarbonize sectors, such as the cement sector, the steel sector, perhaps the paper and pulp sector, are using natural gas today and will continue to use natural gas and to power the global economy if we can get carbon capture and storage properly and fully deployed. The fourth great demand sector for natural gas is a new demand sector for the manufacturing of hydrogen, often referred to as blue hydrogen, creating hydrogen from natural gas, using carbon capture and storage to make sure that emissions are controlled. So we do believe that decarbonization pathways, decarbonization scenarios are increasingly identifying a central role for hydrogen, and that natural gas will be one of the major feedstocks to produce that hydrogen. Again, alongside renewable power, which can also be a significant source for hydrogen production as well. And then finally, not to forget that natural gas has a very strong card to play in providing clear skies and clean air because of its low pollutions that are involved in the clean burning of the blue flame. And here I particularly highlight the ability to clean up emissions from trucks in urban areas and also from ships in the high seas. Let's just take a quick look at the kind of impact that these 5 measures could have on decarbonization. I won't go through all the numbers, but here we've taken some indicative cases of shares that natural gas could take and could contribute in each of these decarbonization methods, show the incremental gas demand on the top and the emission savings that are connected by doing that. So, for example, we identify approximately 300 BCM a year of additional gas demand that could be available if we were to displace just 20% of Asian coal-fired generation, and that would give you over 0.5 gigatons of savings there and there. In fact, 680 million tons of savings. The savings from electric vehicles in terms of emissions, much smaller. The big emission savings are very much coming from the coal displacement more than the oil displacement. And you can see big opportunities there in CCS and big opportunities potentially in hydrogen, depending upon the assumptions taken. Now, let me move on to say a quick word about the emission pathways that are available. It's very important that we try to move down an optimal emission pathway. If we look at the chart here, it's clearly far preferable as we move from 37 gigatons in the energy system to a net zero, that we're on that lower green trajectory rather than the higher light green trajectory. But the key point here is that it is early action with natural gas that can help us move to that better emission pathway. If we focus too much on the next generation technologies and the 2050, 2060 target dates, we are concerned that we may end up on a trajectory close to the higher one illustrated here. So I think it's a very important message to take to policy makers to push natural gas in the early part of the period to get the full advantages of taking early action. Now, that raises a concern, and a very important concern. It's often said, but if you do that, are you leading to a lock-in of fossil fuel emissions? And here we believe, again, it's very important to think through how the energy system can operate and how it can transition. And in our study, A Sustainable Flame, we illustrate and we argue very strongly that gas infrastructure can be an enabler to move us from a world of unabated natural gas to a world of abated natural gas and other types of gases. So to get the benefits of this early action, we're going to meet energy demand growth with clean natural gas. We're going to substitute from high carbon fuels to natural gas. And we're going to start generating hydrogen with the technology we have today of steam methane reforming. Moving forward in time, we can convert a lot of the gas infrastructure, whether it's pipelines, whether it's storage, whether it's liquefaction facilities, they can become the enablers for new forms and new technologies of gas. We can retrofit or put in carbon capture and storage on many units. We can convert natural gas units to run on hydrogen or on ammonia. We can certainly blend in biomethane or renewable natural gas. And we have the option of synthetic natural gas. So we believe that there's a clear transition that is possible, not just in the power sector, but also in the gas sector to reduce the emission intensity of the blend. So let me sum up for you at the end of this presentation. I hope the message has been clear. Gas will become the second pillar of decarbonisation alongside renewable power. Why? Because there are parts of the world and parts of the economy which will be very difficult to service with electrification, direct electrification and wires. Using gas and using pipelines can help us get further and reach more parts of the economy. Early action based on the use of traditional natural gas can have a really big impact. We must minimize methane emissions, but so long as we do that, the impact of early action can be significant with natural gas. At the same time, we need to invest for the future, and then we bring in hydrogen, carbon capture, renewable natural gas, and this can be done without risk of emissions lock-in as we repurpose the gas infrastructure. Just mentioning to close that, of course, the timing and speed of this transition will play out in different ways across different continents, across different countries, across different regions. And it's very important to bear in mind that some regions, perhaps the most developed, some of the most developed economies in the world, will be moving to this deep decarbonization stage, moving from unabated natural gas to new different types of gases, at the same time that parts of the emerging world and emerging economies will be introducing more natural gas in the mix as a form of decarbonization. Thank you very much indeed for your attention.
Thank you very much. Hello from Perth, Australia. I'm very pleased to deliver a presentation to this Future of Energy event. My topic is about the growth of natural gas and the liquefied natural gas LNG industries. Of course, gas is a major competitor of coal, primarily for electricity generation. So right away, I'm going to move to an outline of the presentation. I begin with an assessment of the past and future energy mix, that is the combination of resources that satisfy total energy demand. Then I focus specifically on the rise of gas and the decline of coal and the possible benefits of that. Next, I cover the gas resource prospects, including for unconventional resources. This is a major reason for the rise of gas. And that's followed by discussion about the gas and LNG market structures around the world, how they're evolving and forming prices, since price is a very important determinant of demand and supply of natural gas and competing resources. And finally, I discuss the rising LNG competition around the world, including the major role played by Australia in that area. So we start with the energy mix. This figure shows the historical energy mix and a forecast to the year 2040. We can see, first of all, that coal once upon a time captured 70% of energy consumption. Then the oil industry was born in the 1800s. It would eventually capture 40% of the market and then go into decline. Note that this doesn't refer to the absolute consumption of oil in barrels. That continues to rise today. It's just the market share that reached a peak in the 70s and has been in decline. And you can also see the rapid penetration of gases into the mix. In this methodology, that includes natural gas or methane, as well as renewables like solar and wind. But mostly it's natural gas. And the reason for the rise is its many benefits, such as its abundance, its affordability, its wide geographical distribution, and its environmental advantages, at least compared with the other fossil fuels. So continuing on with this theme, I like to give the case study of the US experience. They, of course, had their unconventional tight shale gas revolution starting in the mid-2000s. You can see how production rose steadily over the years, and that brought gas prices down in that country, and they've remained at very low levels ever since. In this next figure, again, we see the same gas price series, this time compared with the price of coal. When you have competing resources, sometimes it's the relative prices that determine the winners. So with the gas price falling below coal at times, it means that gas becomes more affordable to consumers, so you would expect gas usage to rise. And precisely that has happened if we see in this figure that the declining gas price led to a decommissioning of coal-fired power facilities and their replacement by plants run on natural gas. And that is part of the reason why CO2 emissions in the US have fallen to levels not seen since the early 1990s. Now, of course, the year 2020 was a different story. That's due to the pandemic, but even in the few years before that, CO2 had fallen. You can see how the peak occurred around 2005. That's when the shale gas revolution really got going. If we focus just on the gas outlook, this is from OPEC's World Oil Outlook. I used to work on this report every year, and we can see in the growth column how coal experiences negative growth over the next few decades, whereas natural gas is the fastest growing of the fossil fuels. But it's really the renewables that will see the fastest growth. However, that's coming from a very low initial base. And in the final column, these are the percentages of the total market. If you were to add up all of the renewables together, they account for 27.5% of the energy mix. And that's the same as the share of crude oil by the year 2045. So looking at some of this information graphically, again, we can see that natural gas and renewables are the fastest growing in the coming decades. The other major takeaway from this figure is that virtually all of the world's future energy demand growth is coming from the non-OECD. So that's represented by the less developed countries or the emerging countries. So for these places, it's more difficult for them to finance an energy transition. Therefore, natural gas could play an important role in those regions. Now, part of the reason for the optimistic outlook for natural gas is due to the abundance of the reserves and resources. This figure shows the evolution of proved, mostly conventional gas reserves in the world. And already by the year 2000, you can see that the reserves were heavily concentrated. And this is true today as well. So they're mostly located in the Middle East, primarily Iran, and also in Eurasia, and that's mostly Russia. If you were to compare this with the unconventional resources, there's a striking difference. This is from a study published in 2015 that estimates a global recoverable shale gas total of nearly 7,600 trillion cubic feet. That number is roughly similar to the proven gas reserves around the world. But this study left out some important shale-bearing regions like the Middle East and the Caspian, so these numbers must be far below the truly global level. Nevertheless, the resources are widely distributed, with China accounting for the largest share at 15%, followed by Argentina, 11%, then Algeria, 9%, and the US and Canada, 8% each. If we focus just on Argentina, you can see that it was estimated to have recoverable shale gas of over 800 TCF. That's a huge number when you compare with the proved gas reserves of the country of just 13.6 TCF. So this could potentially be a very important source of supply, both for domestic requirements and can also feed into the export projects. Of course, it's one thing to have abundant resources, another thing to be able to access them. This slide highlights some of the key considerations for successful shale development, ranging from the necessary favorable geology to the required infrastructure. And if you go down the list, for example, to regulation, it's important for governments to provide incentives for development. If they are, for example, regulating prices, it could disincentivize exploration and production. And then the final 2 points on the slide, environmental impact and public acceptance. These are very important for a nation's so-called social license to operate. We've seen around the world that without that social license, development becomes very difficult. That's due to the concerns around the extraction methods, hydraulic fracturing, which have aroused widespread environmental concerns. There you see them: intensive water use, contamination of drinking water, emission of greenhouse gases, and induced earthquakes. My investigation into this shows that there are indeed environmental hazards, but that most have been overcome as the industry matured and as regulation, environmental regulation that is, was introduced and sharpened. Of course, there's also the risk that an overly demanding regulatory regime, which is caused by sometimes alarmist environmental groups and then supported by unreflected media reporting, that could impose costs that hurt the industry in the future. So there's a trade-off there. I move now to a discussion of the different market structures and price formation around the world. In this price series, first of all, if we look at North America, US Henry Hub at the bottom, prices remained very low. That's because gas prices in that region reflect the fundamentals of supply and demand of gas itself, so-called gas-on-gas pricing. In other regions like Europe and Asia, the markets are less developed, there's less buyers and sellers, and they had to compare their gas prices to another global energy source, in this case, crude oil. So that's why gas prices in Europe and Asia rose and fell together with the price of oil. I don't have an index here for Latin America, which has hybrid markets of competition, also oil indexation, regulation in some cases where governments determine prices. But in any case, as global gas trade continues to expand, it brings the different regions into more direct contact, and that could lead to continued convergence of relatively lower prices. It's not necessarily the case. For example, we see an outlier here in 2021 that was caused by an exceptionally cold winter in Northern Asia, and that's for a competitive market-based price, the Japan-Korea marker. So both have their advantages and disadvantages. The market-oriented prices tend to be a bit lower, but they are volatile. The oil-indexed prices, which are negotiated bilaterally, tend to be more stable, but often a bit higher. And you can see in the next slide how market-based gas-on-gas pricing has been on the rise over the past decade, but the progress is not that quick, and it varies by region. As mentioned, North America is competitive, Europe has become competitive, but Asia is still lagging, partly because it requires transportation over water, so LNG is necessary, it's very expensive, and some producers in that region have a desire for longer-term oil-indexed higher prices. It gives them the confidence to be able to invest upfront in the very capital-intensive LNG infrastructure. But despite the different markets, you can see, first of all, in the little figure on the right, that LNG exports in the world have gone up almost 4 times over the past 20 years. And on the left, you see that Australia was the #1 LNG exporter in 2020, followed by Qatar, which had been on top for many years before that. And the USA, which was off the charts just maybe 6-7 years ago, is now a major exporter. Again, that's because of their shale gas revolution. Here we see more focus on Australia. Most of the LNG comes from the state where I'm located, Western Australia. There's also LNG from the Northern Territory and from an eastern state called Queensland, where coal seam gas or coal bed methane is the major gas supply for the LNG. There was around $200 billion of investment, mostly during the commodities boom that started in the mid-2000s. And Australia is in a good position, being located in the fastest growing region on Earth, Asia, so it can export with lower shipping costs. Most of the LNG from here is indexed to the price of oil. And the final point, I haven't mentioned hydrogen, that's a different story, but certainly lessons are being taken from the design and the execution of LNG projects in this country, where there were cost blowouts and delays often, and the lessons are being applied to a hydrogen export industry. Here we see the LNG again by project, and it shows how Australia quickly became the world's largest LNG exporter, whereas Qatar remained flat for a long time, but that was due to a moratorium on the gas field that supplies their LNG. They now have plans for expansion. You see it here. First of all, on the left-hand side, Australia, Qatar, US will be competing for the top spot in the coming decade. And on the right-hand side, though, you see that Australia does not have much of a capacity expansion plan for the next 5 years, whereas Qatar certainly does, and so does the US. And the final point there is that the low-cost producers like Qatar may be able to undercut the higher cost producers like Australia by offering lower prices to consumers. So against that background of competition and lower prices and abundance, improved productivity is seen as vital. And as I mentioned, most of the investment in Australia, for example, came online, the projects did, when prices were very high, but then they entered a much weaker market than they had anticipated. So what they're doing now is reducing costs using some of these options, better early stage planning, cooperation between companies, standardization of equipment, and the introduction of flexible technologies like floating LNG, which is less costly and much simpler than the massive projects of recent times. Also on the consumption side, floating import infrastructure is being considered or is being developed around the world. This enables, for example, less developed countries who don't have the financial scale to construct the massive onshore import facilities, the opportunity to increase their gas usage as well. And I close with a slide that extends the energy mix shown earlier, this time to the year 2150. So it looks a bit science fiction-like at this stage. But anyway, it shows that the market share of methane, natural gas, reaches a peak in 2050. That allows for sufficient time to develop non-fossil sources. And indeed, natural gas can lead to widespread development of renewables, intermittent ones like solar and wind. Also, hydrogen may be derived eventually from various of the non-fossil sources shown here, also the fossil nuclear as well, but it's all very uncertain and will depend to a large extent on policy, technological, and economic factors. So I go to the conclusion slide. First of all, it used to be the case about 10 years ago that natural gas was a bridge towards a low carbon future. Just in the past 2 or 3 years, I'd say gas has become fairly unpopular, mostly in the industrialized world because it's still a fossil fuel. Nevertheless, the rising LNG and pipeline capacity is bringing the world together and leading to an increased global market. Despite that, regional price differences are likely to persist for several decades. First of all, because of the distinct economic market structures around the world. Also, because the cost of transportation, in the case of LNG, it's expensive. That has to be included in the price. And finally, both producers and consumers desire long-term security and stability. The producers want security of demand. The consumers want security of supply, even if it means slightly higher prices. So with that, I conclude the presentation. I thank you very much for your kind attention, and I'll look forward to any questions you might have later in the session. Thanks again.
Good morning. My task today is to talk about carbon capture and storage as part of the energy transition that's underway now in the world. It's clear that the negative impacts of climate change are with us now. Those of us who live in California are certainly seeing them. And we really have to reduce our dependence on fossil fuels. So that implies the following question. How do we supply the energy the world needs to support a growing population in modern societies at the same time that we reduce greenhouse gas emissions dramatically? So this is a topic that the International Energy Agency has looked at, well, repeatedly, but most recently in a study of how to get to net zero by mid-century. And they point out, and that, as we all know, that there are lots of parts of this. We need to spend a lot of effort on energy efficiency. Energy we don't use doesn't have emissions. We need to invest in renewables like wind and solar. Those are cost competitive now in the best resource places. There'll be some switching from coal to other fuels. Nuclear will play a role, but because the costs are relatively high, it will be small. And the IEA study indicated that that carbon capture and storage can enable these pathways in a way to deal with intermittency and at reducing the overall cost. So the question is, all right, how do we do that? So CO2 emissions from energy are about 36 billion tons a year of CO2 now. So we could think about capturing those from concentrated sources like power plants or from directly out of the air, but the concentration of CO2 in the air is much lower, and so that's a more expensive separation. Even so, there are lots and lots of ways to capture CO2. It's actually done all the time at commercial scale in refining and fertilizer manufacture and in some other applications. There are a variety of ways to do it. You can, I'll talk about just one of them. Solvents are usually used now in natural gas separations, and there are a variety of electrochemical and thermochemical methods as well. So capture, we can do it. It costs more than we would like, but it can be done, and it is done now. So then the question is, all right, what would you do with the CO2? And you can, in fact, from CO2, make fuels. You can make synthetic natural gas. You can make materials, you might make minerals, and then it can be used for enhanced oil and gas recovery in geologic formations. That's the biggest use now. There are also some storage options in geologic settings, and then many ways that biological systems capture CO2 and then turn them into something else. So there's a lot of opportunities to do this, which is good because we're going to need to apply lots of different methods to do this in a good way. So one example of an advanced process that would capture CO2 is a power plant that there's a demonstration version in action outside of Houston, Texas. The basic idea here is that supercritical CO2 is the working fluid in the turbine rather than steam or combustion product gases. To do that, they separate pure oxygen from air, burn the natural gas here. That drives a turbine. Downstream of the turbine, the product gases, which are CO2 and water, are cooled to knock out the water, and then compressed again and recirculated to be heated and driven through the turbine again. Now, you can't keep adding CO2 forever. You obviously have to take some CO2 out to balance the system. That's done at the high pressure side here, so that's ready to go off to be stored. The advantage of this is the additional cost of capturing CO2 here is very small, but the cost of that's paid for, of course, in the air separation unit upstream. The estimates of the cost of electricity are that it's competitive with natural gas power generation, that the efficiencies are pretty good, near 60%, it at least offers the possibility of continuing to use natural gas for firming power generation when wind and solar are not available. The other end of the extreme is capture from the air. This is one example, a company called Direct Air Capture. The company is Carbon Engineering, and they're doing direct air capture. They use potassium carbonate, potassium hydroxide solution that captures the CO2, makes a solid pellet, then they heat that to recover the CO2, and then separately make hydrogen from electrolysis and Fischer-Tropsch synthesis to make a liquid fuel. And they say the cost could be around $100 a ton for the capture. It's worth remembering that every conversion step has an efficiency less than 1, and every step has a substantial energy cost as well. So it takes lots of energy to do this, but it can be done. And to do this at scale, of course, we'll need to reduce the costs. Biological systems also move very large quantities of CO2 around the planet. We can take advantage of those by reducing deforestation, from growing new forests in some places, restoring soil carbon that's been depleted by modern agricultural practices. And then there are assorted biological capture systems, including one version which takes the biomass, burns it to make electricity or fuel, or makes fuels, and then applies carbon capture and storage to make a negative emissions technology. Estimates in some studies say that maybe as much as 5 billion tons a year of CO2 could be captured at less than $100 a ton. So once the CO2 is captured, then of course you have to transport it to where it might be stored. Pipelines are the preferred way to do it. The technology is well established. There are large CO2 pipelines already for enhanced oil recovery. But we will need hubs and networks to do this at gigaton scale. There is one version of a project out that uses ship transport of refrigerated CO2 to transport it to storage sites in the North Sea. That's the Northern Lights project. Truck transportation can be used for pilots, but it's too expensive for large-scale operations. So where might we put the CO2 if we do this? Oil and gas reservoirs are an obvious place. There's a lot of experience since about the early 1970s of injecting CO2 for enhanced oil recovery. An oil and gas reservoir has the primary advantage that there's a seal that kept those buoyant fluids in place. And so it's a place that will contain the CO2 indefinitely. To do this at really big scale, we'll also need deep formations that contain salt water. Coal beds and shales are possibilities because CO2 adsorbs on those as much as it does with methane. And of these storage types, of course, only the enhanced oil recovery is in operation at any real scale today, because that has economic value. It should be said that the storage capacity worldwide is quite large compared to the kinds of volumes we might be talking about. So the storage resource is not really an issue. This picture shows oil and gas basins in blue and saline aquifer basins in the kind of orange color. And indeed, most oil reservoirs have water underneath them as well. So there are lots of options. Not all of these rocks will be suitable because of various reasons, but there does seem to be a abundant supply of storage locations. So the question then is, well, all right, will it stay there if the CO2 is injected? And the answer is, in a well-designed system, yes, it will. The seal rocks prevent vertical migration initially. Water that comes in and invades the CO2 area leads to trapping of bubbles of CO2 in the rocks. These are done by capillary forces, and those are very hard to move once they're trapped. Because CO2 dissolves in water or in oil, it increases its density. It takes less volume when it's dissolved, and so that means that water invades the area that where the CO2 has been sitting, and so therefore there is this residual phase trapping that takes place. The CO2, of course, then continues to dissolve. It actually makes a mixture with water that's slightly more dense than water without the CO2, and that leads to a reduction in pressure and also a driving force for the CO2 to go down instead of trying to go up. Mineralization is also possible in basalts, particularly. They're often slow, but they are permanent. So what about using the CO2? Well, if you think about what kinds of things we use at the scales where we make CO2, one is obviously fuels. Making fuels directly from CO2 is an energetically expensive process. So it currently takes 3 to 4 times as much energy to make the fuel as you'll get by burning it. Biofuels, of course, do another version of that, but fuels are certainly one possibility, though cost competitiveness is an issue. If solar and wind electricity are available at low enough cost, and in good places they are available at these kinds of costs now, making a liquid fuel might be possible with abundant power generation. Construction materials are like cement are another place that CO2 is used, and then chemicals are smaller, and in all of these cost competitiveness is a primary issue. It will take very large new systems to be able to do this at big scale. So what about markets for CO2? Well, the current global market is about 80 million metric tons per year. That's a long way from the gigaton scale. About 50 million tons of that is used for enhanced oil recovery, and the rest mostly for food applications. Most of that CO2 now comes from separating CO2 from natural gas. And then 13 of the 17 big projects around are for enhanced oil recovery. Aquifer injection is 4 projects. Large-scale CCS will require a really large effort, significant investments in financing, alignment of the industry and various kinds of industries around clusters, creation of pipeline networks, government participation, and indeed public acceptance as well. The public will accept this only if they can be convinced that it will be safe. And the volumes of CO2 are very large. If you think about 3 billion tons a year of CO2 and convert it to the typical density in the subsurface, that's about 100 million barrels a day of injection. That's about the size of the oil production industry now. So do we engineer systems at that scale? Yes, absolutely. But it is very big scale. And so that means that carbon capture and storage can only be one element of economy-wide efforts to reduce greenhouse gas emissions. In terms of global projects, there are quite a few in place, some bigger than others. The big ones here are 5 million tons a year. The blue ones here are being planned, If all of these projects go forward, that would be 175 million tons a year in addition. It's a step in the road, but obviously it will take many, many more projects to get to the gigaton scale by mid-century. So let me conclude then. The portfolio of CCS technologies is well enough developed now that deployment at scale is feasible if the cost issues can be resolved. CCS should be one of the broader, wide-ranging portfolio of technologies we apply for greenhouse gas reduction. Lots of capture technologies are available, but only a few have been really widely deployed, mostly the solvent methods. People are working on research on negative emissions, that is, taking CO2 that's been in the air and storing that away. We'll need those if we don't do better on reducing CO2 emissions now. Direct air capture is doable now, technically, but it certainly is costly. It's worth noting that none of this will happen at big scale without some changes like a carbon price, emissions regulations, continued subsidies, as well as a concerted effort to build the kinds of infrastructure, hubs, clusters, and pipeline facilities that will be needed to do this. The subsurface expertise of the oil and gas industry is going to be required to be able to pull all this off. These are skills that are resident in that industry. So with that, I'll close and thank you very much, and I'll be pleased to respond to questions.
Well, good morning. I would like in first place to express my gratitude to the organizers of the Engineering Congress, in particular Engineer Solanet, President of the Argentine Engineering Academy, and Engineer Oscar Viñar, who's also Director of the Academy and President of the Congress. What we will be discussing today in these 14 minutes or 15 minutes that we have designed is what this new term that has been coined quite recently means, nature-based solutions, and how important that could be for the development of Argentina, in particular, its energy industry and its ecosystems, in particular, natural and productive ecosystems. Nature-based solutions, as I just mentioned, is a quite recently coined term. It appears and is defined for the first time around 2016. And this happens because of what had been discussed at the COP21 in Paris and the Paris Accord. So according to the International Union for the Conservation of Nature, it has to do with actions to protect, sustainably manage, and restore natural or modified means productive ecosystems in a way that's effective and that adapts while at the same time provide human well-being and biodiversity benefits. But this is not about discussing definitions of terms, but actually it has to do with a discussion that two organizations, one is the Argentine Academy of Engineering and the other is the Argentine Center of Engineers, to which I belong, have been discussing for the last year. And this will be presented later, we think this year or eventually next year, in a document that's called, as it said here, Considerations on Possible Institutions and Regulations to Achieve an Efficient Transition of the Argentine Energy Industry by 2050. So the main objective of this document is to design a transition towards 2050 and these scenarios for the sector to achieve net zero emissions. But at the same time, to support the development of nature-based solutions having in mind a secondary objective. And this secondary objective or complementary objective is thinking that since Argentina has quite vast natural gas resources, that these resources could be developed for the development of the Argentine economy and society, but also to create an opportunity for net zero emission natural gas to be exported to the countries that are willing to demand this type of product that will have an additional value, but at the same time an increased cost that would support the development of these resources in Argentina. So let's discuss a bit how important the nature-based solution sector is and how it has to move from being today a source of emission of greenhouse gas emissions into the future in being the opposite. So this chart here, what it shows us is the global emissions from different sectors. As we can see, the agriculture, forestry, and land use change sector is around 27% of global emissions. The rest, of course, is mainly caused by burning or the consumption of fossil fuels. Within agriculture, and this is where the change from emission into lower emissions or sequestration must happen, and that's the scope of nature-based solutions as we just presented, we can see that there's different activities that generate emissions. The main is the enteric fermentation process within ruminants, then deforestation, rice, manure management, etc. But we think that this is very important to understand because one of the concepts that we constantly hear and that we have discussed extensively with Engineer Oscar Viñart and Engineer Badaraco and other experts within the Academy is that many times CO2 is seen as a polluting gas. And we think that it's more important actually to understand that life on Earth, as we know it, depends on the cycling of that CO2 and depends heavily on the existence of that gas in the atmosphere. It's a very small part of the atmospheres of the atmospheric gas content, but nevertheless, it's a very important gas. So we have depicted in this chart is the total cycle of carbon in its different forms, because there's a moment when it is a CO2, but then it's transformed into other types of molecule, including organic molecules within living organisms. So the total emissions that come from nature are 771 gigatons of CO2 per year. When we look at total fossil fuel emissions caused by human consumption or anthropogenic sources, it's 35 gigatons per year. Land use change and other agricultural emissions account for 6 gigatons per year. And that gives us a total of 811 gigatons per year of total emissions that come from, as we said, natural sources that occur with humans or no humans on this planet, and the real anthropogenic emissions that account for 41 gigatons of this total. At the same time, these emissions don't just remain in the atmosphere as if it was a balloon filling up with air to eventually one day explode. But on the other hand, these emissions are also going back into terrestrial ecosystems in the number of 454 gigatons. The oceans have also been sequestering or absorbing CO2 for the different cycles of life within the ocean in a relevant volume. And this all adds up to 791 gigatons of CO2 per year. But there is a certain percentage that remains in the atmosphere, not being absorbed by terrestrial or by the water bodies of the planet. And this is what's been causing the stock problem that we have that we call climate change. This comes from different documents, but the main document where this comes from is a group of scientists originally from IPCC that have been publishing for almost 10 years what's called the Global Carbon Budget. And this group that was originally led by Corinne Lecker, and what they show us is how emissions and absorptions work on this planet. This chart here shows from the year 1900 until last year. This was published this year in 2021. And as we can see, the line above the 0 is emissions, that is mainly in gray, fossil fuels, then land use change, and below 0 is where those emissions go to. So we have the oceans, second, which are suffering from these emissions to acidification. Then we have in light blue the atmosphere, and in between what we have is the terrestrial ecosystem that actually are improving because of this presence of increased CO2 and their absorption. So again, it's important to understand both the stocks, which on this chart of the FAO's global recarbonization program that we happen to be part of are depicted. And on the right, we see the flux of CO2 with total emissions on 41 gigaton of CO2 equivalent per year. But what's important to see here is that not only there are anthropogenic emissions happening annually today, but there has been a huge loss of soil carbon over the 10,000 years that humans have been doing agriculture, accounting for around 135 gigatons of CO2 equivalent that have been lost from emissions to the soil, from tillage done to soils. So when we think of stocks, and it's also very important to think that in most cases stocks are being accounted for in carbon, but it's important, as I put on the left-hand side, to think of them in CO2 equivalent. And what we see is that when we add the total stock of carbon that's in soils, of course not in the form of CO2, but in other molecule types, and we compare it with the atmosphere holds between 1/3 and 1/4 of the total stock that is in the other sectors that we just mentioned, soils and biomass. So it's important to understand these numbers to see how these ecosystems and soils can provide a solution for the developments humanity needs for the next decades. So when we think about nature-based solutions, we can divide them in 3 different groups. The first group has to do with activities having to do with forests. For example, avoided deforestation or planting trees like reforestation or afforestation. The second group comes around agriculture, so annual crops, perennial crops of all types, and grassland management. And the third group is around wetlands. So in all these cases, when we analyze each one of these technologies, and we don't have the time today, there happen to be benefits not only to greenhouse gases, but also to other services that humanity requires from nature, like biodiversity, water quality, air, etc. This the total capacity of these technologies, if deployed globally, would be annually in around 23.8 gigatons of CO2 per year. Let's remember that annual emissions today are around 41. So nature-based solutions could supply an important number of that if fully deployed. But on top of that, we must think that agricultural value chains also have emissions downstream and upstream. If we change, or if we took in consideration the downstream aspects of global value chains, for example, by improving diets, by decreasing food waste, or by replacing fossil fuel or emitting energy sources, or increasing overall efficiency in this value chain, we could also increase that capacity from around 0.7 to 8.5 gigatons of mitigated emissions per year, which shows again how relevant the nature-based solutions is as an activity that happens in ecosystems, but also along the value chain, because humans will continue to eat and we haven't learned how to live without eating. When we go into the detail of different technologies, and this is a list done by McKinsey & Company, where we can see very specific type of activities, and I've divided them in 3 groups. The gray group has to do with efficiency in energy use or farm machinery with lower emissions. The green one has to do with nitrogen fertilization and its emissions, which is a very important in agriculture. And the third group, the light blue, has to do with animal production. When we see the cost per ton, we see that there's a very important group that's above zero. That means that actually applying these technologies, it requires an investment, but there will be an economic profit coming from it. That's why it has a negative cost. On this side, on the opposite, these activities do have a cost, not only in its deployment, but also when they are annually developed. But we see that there's a big number. For example, one that I wanted to mention today is the reduction of over-fertilization in China and India. Many countries subsidize nitrogen fertilizers, and there's been a surplus in their use and a wasteful vision of how they're being applied. And this would create a great benefit, having a negative cost of $97 per ton of CO2. So instead of paying, well, this would create a profit. Well, analyzing and reaching our final slides, this slide here shows us the Argentine National Inventory of Argentina in its 2017 publication, which is the last until today. And as we can see, the different sectors, and starting by animal production, have different, is number one. When we think from this inventory today, what could be the possible solution coming from nature-based solutions? We think that Argentina could reach zero deforestation, avoiding deforestation, but increasing reforestation and conservation of ecosystems. We could improve our management of dung and therefore decreasing methane emissions, improve fertilizer use or decrease it, and sequester carbon in forestry, and also to a very large extent to increase sequestered carbon in soils. We think by the time we publish the document, there will be numbers to each one of this estimating their potential. But what we're finding is that's close or more than the total inventory in 2017. So to express our final conclusions, well, we think that Argentina needs investments both in its energy industry and its productive and natural ecosystems to reach its development and sustainability targets, both expressed as SDGs or the Paris Accord aspects. So zero emissions natural gas is possible with nature-based solutions during this energy transition period for a country like Argentina that combines both extensive natural resources, natural gas, and at the same time, a very vast surface of land that requires improvement. So additional positive externalities will be created by this type of alliance, like employment, energy security, trade balance, large-scale ecosystem restoration, improved agricultural production, and experts coming both from natural gas and agriculture. So this, I believe, is an engineering, sustainability, and economics challenge that will only be solved if these two activities, these two industries, work together shoulder to shoulder. So, well, thank you very much. And I'm available for questions or comments.
Good afternoon, good morning. Here we are after listening to all this wonderful and very interesting presentation. So now here we are with all the panelists and speakers that gave us this extraordinary presentation. I have some questions I will try to do in order, and then we come back again. Perhaps someone will be for both of you. The first one is for Bassam. It is according, Yves Bamba asked, the meaning of burden sharing mechanism you mentioned in your presentation. Could you explain or define a little more what is the meaning of the burden sharing mechanism?
Well, first of all, thank you, Roberto. It's really a great pleasure to be here. I think there are two dimensions to answer that question. I personally think that a key feature of climate change that is not always appreciated enough is the unevenness of its impacts on countries and regions. This is not only in terms of the physical impacts of climate change, but also in terms of the economic adjustments which are needed to reduce emissions and achieve climate targets. And some countries, particularly those that rely heavily on the hydrocarbon sector as the main source of their income and export revenues, will have to undergo much deeper adjustment and transformation. And this even applies, to the group of oil and gas exporters, because there is this idea that oil and gas exporters are very rich countries. And actually, this is not the case. There are some in a better position to cope with the challenge of reducing their emissions and investing in low carbon technologies. It's well established that the climate policies can also cause substantial distributional effects and a reallocation of wealth. And at the end of the day, oil and gas exporting countries are expected to experience the decline in their incomes and wealth as the demand for their key export product is projected to fall. So if you believe in just an inclusive transition, I think this dimension actually need to be recognized and addressed. But even if you don't want to recognize that dimension, Roberto, I think, which I think is very, very important, of course we should recognize, but even if you want not to do so, I think, from a global dimension, and, I mentioned my presentation about the CCS, because the deployment of CCS is needed to help achieve the goal of net zero emission, given that oil and gas are projected to remain part of the energy mix, at least for the foreseeable future. And also for some energy-intensive, hard-to-abate sectors, such as steel and cement, technical options to reduce emissions without CCS are currently very limited. And I think the IPCC scenarios make this very clear that CCS is needed if we are ordered to achieve 1.5 degree targets, or if we are able to achieve the climate targets at a reasonable cost. Now, if you bring it to the oil and gas exporters, I believe that oil and gas exporters have a competitive advantage in this technology, given their natural resources. For instance, their geological storage capacities, their access to depleted hydrocarbon reservoir, and their existing infrastructure. But also technical resources, for example, their expertise in subsurface technology. So in a way, deployment of CCS could provide them with an opportunity. But as we know, CCS is a very costly technology. And if you shift all the costs to the producers, this will reduce the incentive to undertake investment in these projects. CCUS projects involve high front cost, high operation costs. There isn't much revenue. The only reason why perhaps you would deploy CCS, is to address climate change. And if all the stakeholders along the oil and gas supply chain benefit from CCS, I believe that the cost of CCS deployment should be shared if CCS is to emerge as a key mitigation strategy. We at the Institute, we have been doing some work trying to explore some of these mechanisms. But certainly, the carbon pricing mechanisms such as ETS or carbon tax, at the moment, these are not enough to incentivize investment. There are additional layers of finance which are needed. And that basically recognizes that we need, a framework which recognizes storing CO2 has a value, which is separate from emission reductions, and that should be rewarded. And I personally think that those mechanisms could be created within Article 6. So if you want an inclusive energy transition, if you want the oil and gas producers to be part of the solution, and many of them are showing that tendency, then we should think outside the box and try to develop mechanisms that enable burden sharing mechanisms.
Okay, thank you very much, Bassam. Can you listen to me? Good. There is another question for the same direction, Yesterday, Fatih Birol talked yesterday about the responsibility of the developing countries in the historical accumulation of CO2 emission. How do you think it should be managed? I think this question is also could be for Michael Stoppard.
Roberto, you want me to address that question?
Sure, I will address this question for you and for Michael. I think
all right, okay.
Both of you.
Well, look, it depends on the type of the transition, and I think for a successful and smooth transition, it requires the recognition of few principles. The first one, that there isn't really a single transition path for all countries, and that countries are likely to follow very different transition paths depending on their initial circumstances. Sure. But also the principle of common but differentiated responsibilities, and also the concepts of inclusive and just energy transition. Also, a transition that is not very costly, because if the transition is likely to result in high cost, this is likely to delay the transition, also its acceptability, and undermine certain principles such as energy access, affordability, or even energy security. And to me, this means not only talking about the cost, but also reallocation of costs and reallocation of revenues and technology towards the least developed countries that are working basically to meeting their commitments.
Okay, thank you, Bassam. I would like to ask Michael.
Well, I would say that there's clearly going to have to be some kind of compromise between the technical, economically most efficient way to decarbonize, the politically acceptable way of decarbonizing, and the cost, the political acceptability, and the timing with which we do it. Now, I think it's generally accepted that the developing economies should be heading in that direction in a later time frame. There will be pressure in the negotiations for that to speed up, and the counter argument will be, well, we have to look then at the historical role that developed countries played in building up to the current inventory of carbon emissions. So all those factors are going to be brought together at Glasgow and beyond in a negotiation. And so I think it's going to be ultimately a negotiation between what's economically efficient and what we can politically agree on.
Okay, thank you. I think that Frank Behrendt was talking about a part of the solution, according to this, when he's talking about a synthetic fuel. So there is some question about, could you identify between synthetic fuels and renewable produced fuel, which is the main decision factor to choose one or to choose the other one?
Yeah, it's a question what you define as a renewable fuel. If this reflects on biogenic fuels,
that's right,
then there's a very clear argument. Because if you look at biodiesel, mainly from oily seeds, or if you look at ethanol prepared by fermentation process from grains, you always have the conflict between food use and a use of fuel. And that is unavoidable because both oils and the grains are obvious, even if you look for some specimen which are not used today as a fuel, as a food, there is a potential to use as a food. So, and if you go to synthetic fuels, having a gasification step in between when you talk about second generation fuels, or if you talk about fuels really going down to hydrogen made from electrolysis of water combined with CO2 from the atmosphere, in the extreme case, the case we had probably reflecting on direct air capture, then you avoid this problem. But there is a clear downside to this. One has to be clear about this. There is a reason that the biofuels became popular, because they were simple. It's straightforward, you can do it, you don't have any technological challenges. While looking at what we are talking here about with respect to synthetic fuels, it's easily a factor of 3 in production cost compared with fossil fuels today. For sure, there is a chance to decrease this price. It will strongly depend on the price of hydrogen. And that strongly depends on the way the electrons are prepared for the electrolysis. But on the other hand, today in Arab countries, if you have a sunny season, which you tend to have, as our colleague from Dubai may confirm today, the production cost per kilowatt hour is in the range of 1.5 or 2 euro cents. And using this to make green hydrogen is straightforward. So what is the benefit? It's carbon free in terms of fossil carbon. It is available everywhere. We have enough water to run an electrolysis process, and the water can be prepared from seawater by desalination based on renewable energy sources again. And you avoid the food and fuel situation, because we will have an increasing worldwide population from today's 7 point and a little bit to 9 point and a little bit in the next 3 decades. So consequently, avoiding any conflict there would be helpful. Whether internal combustion engines will be running forever, I do have certain doubts about this. So the need for the synthetic fuels will also be not in place together. So expecting an extreme good price in, let's say, 5 decades from now may be a little bit too late, because then the engines may not be in place anymore. So it's an interesting game, but for this transition period, for sure it's worthwhile. And for example, a company like Porsche is making synthetic fuels together with people in Chile and imports them to Europe for the first filling of the tank. So things like this are in place already. It's not exotic, it's pricey.
Okay, thank you very much. Of course, we are during the path, during the transition. So according to the technology, Lynn, you mentioned that reaching net zero will be virtually impossible without CCUs, with a world with growing population and with better living conditions. So what could be the highest percentage of participation of the CCUS with respect to the total of action to achieve this objective?
Well, it's a hard question to answer, of course, because it depends on an endless set of assumptions. But technically, there's no question that we can capture CO2 at big scale. We do commercial scale separations all the time, every day, in refining operations and making fertilizer. So this can be done. I think we can get to scales of 1 billion tons a year with substantial effort. The IEA study called for 3 billion tons a year, so it's kind of, it's order 10% of emissions, maybe actually a little more. That's a stretch because it takes such large investments in infrastructure. So there's kind of a difference here between, can we do this, which I'd say yes we can, and will we do this, which depends on markets, on pricing, on competitiveness in all kinds of settings, and on some international agreement that we're going to do it. So those things are harder. So I'd say we can do it at a scale that matters. Even 1 billion tons a year is a contribution that really does matter.
Okay, thank you very much. I remember we have at least 5 minutes. So this is a question to Martin. We are going to talk about actions. So here you have, Martin, a question for you. Does global warming affect natural CO2 cycle? Regarding, for example, CO2 solubility absorption in oceans?
Pardon, can you repeat the question again? I'm not sure I understand properly.
Yes.
Thanks.
Does global warming affect natural CO2 cycle? Regarding, for example, CO2 solubility absorption in oceans? This is the question I have received.
Well, yes, it's clear that as we have increased our emissions, then oceans have increased their their absorption of CO2, and that has been increasing or decreasing pH, increasing acidity. I don't know if that is the answer you were expecting from me.
Yeah, I didn't write it.
Oh, okay, thanks.
So, okay. So for the audience. Right. Now we are going to talk about natural gas. So, Andy, this is a very peculiar question. See, I will tell you, someone from the audience said, Andy, you are very, very eloquent, but affirming that we have not other solution than gas is catastrophic for the mankind, since every ton of CO2 produced this next year will still be present for our children and grandchildren. We have to get rid of natural gas as soon as possible. I would like to ask you, what is your position about this?
Roberto, can you hear me?
Yes, I can hear perfectly well.
This is a great and very human question, and with 3 children myself and with 5 grandchildren myself, I think about the same. Yeah. And I'm acutely aware that my life every year, just by the food that I eat and the waste products that I produces 1 ton of CO2, and you multiply that by 8 billion people, you see where you get. Each of the children that I had also the same, and for the 5 grandchildren. So we need to each understand our impact of our own lives and our children's lives and our grandchildren's lives. And I'm sharing screen for 1 second to say to Eve that each country and globally needs to balance 5 objectives. And those 5 objectives you see on screen is, firstly, that we need secure and available and reliable energy to keep our children alive. They were born, and we on this call today and at this conference, each were born because of the availability of secure and available and reliable energy. That is very clear to me, and in the past it came from hydrocarbons. The second one is that we need to, at the same time, protect the environment and climate and air quality and water and biodiversity, as we've heard at our event. And the third one is that each society from Argentina, but each of the other 200 countries on Earth, need to develop renewables and e-storage, electrical storage, and hydrogen and carbon capture and use. The fourth one is that we need to protect the debt load of future generations. So what is capable in the rate of change, and government to subsidize from the taxpayer the transition, is also limited by not transferring debt to next generations. And the last one is, as Europe is contemplating so harshly and aggressively this week, we need to supply affordable and competitive energy.
Okay. Thank you very much. Very clear.
Natural gas plays that role to help the transition in the process. Natural gas will be consumed today and tomorrow until number 3 will have grown.
Sure. I agree. Roberto, according to this, how Australia will manage the transition to zero emission? It's a producer country with a lot of natural gas. It could be that help, for example, Asia to get natural gas for the power plants, for example. How Australia will manage this transition?
Thank you. Well, Australia is implementing many of the strategies we've heard throughout this session. Currently, there's a conservative government in power who are highlighting gas-led recovery. So they very much see gas as being part of the solution towards a low-carbon future. But other methods include nature-based offsets. There's also excitement around in that area. CCS is a big part of the solution. Australia has ambitious hydrogen plans when you compare with other countries around the world, both using synergies with its existing gas and LNG industries, though primarily the focus is on the development of the green hydrogen in order to take advantage of Australia's very strong solar potential in particular. And finally, large amounts of grants and subsidies are also being dedicated to the development of the renewable industries, which are growing very quickly, already account for maybe a quarter of Australia's electricity generation, and primarily that's solar and wind resources.
Okay, thank you very much. I think that this panel was real pragmatic and realistic according to how to reach the emission zero for 2050. So thank you very much. It was my pleasure to be with you in this panel, and I hope to see you whenever it comes in Buenos Aires. See you. It's my pleasure.
Take care.
Thank you.
Yes.
Thank you.